name's Maddie. I've been working here since September. And so today I'm going to be talking about dark sirens and the effects of galaxy catalog. Before I jump into what those words mean, I wanted to give a little bit of motivation. So the motivation is everyone's favorite crisis in cosmology, the Hubble tension. So as you all know, there's a current 4 to 6 sigma, depending on who you ask, tension in measurements of the local expansion rate, or H. Independent measurements, meaning measurements that are independent from the cosmological distance ladder or from CMB measurements, have been posited as a way to try and break the tension, or at least provide some insight maybe into its causes. And this is where gravitational waves come. So gravitational waves are very unique cosmological probes because their waveform directly includes the luminosity distance to their source. So when LIGO detects a gravitational wave, a waveform that looks like this, that tells us the luminosity distance to its source. So a distance that is independent of the cosmological distance ladder, which makes it very useful. So then, if we know the redshift of the gravitational wave's host galaxy, you have distance, you have redshift, you get H naught. Unfortunately, the picture isn't quite this simple. This is a little bit better. Gravitational wave localization volumes can contain anywhere from hundreds to hundreds of thousands of galaxies. And so if you don't have an electromagnetic counterpart that can help point you to which galaxy is its host, but there's no way of knowing which of these many galaxies the gravitational wave can actually be located in. So then what's the correct redshift? In gravitational wave cosmology, we made distinctions between 2 types of gravitational waves. You have what we call bright sirens, which is our gravitational waves with an electromagnetic counterpart, which are rarer than we would like them to be. And then you have gravitational waves without an electromagnetic counterpart. We call these dark sirens. And even with dark sirens, we can actually still work out cosmology, so it's maybe a little bit more difficult. And that's called the dark siren method. So when we don't have an electromagnetic counterpart that can tell us what this galaxy is, instead we treat every galaxy in the localization volume as a potential host galaxy that can then provide a measure of H naught. And we use galaxy catalogs to get the redshifts of all of those potential host galaxies. We then combine results over all of the galaxies in the volume to draw a posterior H naught. So it looks a little something like this. So let's say this blue histogram is the redshift distribution of the galaxies in our localization volume. And let's say we have a gravitational wave event that occurs at this redshift here. We then use all of these galaxies to say, what if the gravitational wave event happens here, here, here? What is the H naught that we get out of that? And then we can draw a posterior on H naught. So you can see, this isn't that helpful. So we don't learn a lot from one gravitational wave event, one dark siren, not that. But we can combine results over multiple gravitational wave observations. So if we also got lucky and had another gravitational wave event in the same localization volume, say at this redshift, then we draw another posterior. And then we can keep playing this game, we keep adding posteriors, the more gravitational waves that we detect. So let's say we had 200 gravitational wave events in this localization volume, then you draw a posterior that looks like this. And now we've actually learned something about cosmology. So that's a brief intro to what a dark siren method actually is. And in order for this to be useful for cosmology as we continue to have more and more gravitational waves, we need to iron out all the systematics. And so one of the questions that I've been focused on is the problem of catalog incompleteness. So this method relies really heavily on galaxy catalogs. So that poses a problem. Every galaxy catalog is inherently incomplete, right? You're never going to see every single galaxy in that region of the sky at all redshifts, right? Everything's magnitude limited. So if we are missing the true host galaxy, it's not in the galaxy catalog we're using to cover that localization volume. Does this bias our results on H naught? How complete does a catalog really need to be in order to be useful for dark siren cosmology? These are the questions that we're going to answer. So to start off, we're going to start with a simple test case and say we have one localization. So I took the simulated galaxy catalog MindStat and I drew a 1 squared root line of sight in it. That's optimistic. We don't actually have localization volumes quite that small, but this is a good test case. I then injected 200 gravitational wave events randomly along this line of sight, all with luminosity distances less than 1550 megaparsecs, and with varying uncertainty on that luminosity distance. As we increase that uncertainty, it's kind of analogous to the increase in the localization fault. And that 1550 megaparsecs corresponds to about a redshift of about 0.3. So that's consistent with current LIGO-Virgo-Kagra detection capabilities. We then can perform the dark stack analysis. So to test incompleteness, I started by throwing away 90% of the galaxies. So you just get rid of most of that blue histogram, and I kept the 10% brightest galaxies. Where a bright galaxy, here I define using the I band absolute magnitude and G band absolute magnitude. I band and G band trace stellar mass and star formation rate respectively. So I did this so we have two different populations of bright galaxies. Kind of see is one bright galaxy better than another for the star stack analysis. So using only 10% of the galaxies to actually try to make this posterior H naught, what do we get? So here's what those results look like. So this top one, that's the best localized, and as we go down, we're increasing the luminosity distance error, so getting worse localization. And so for the best localized events, as you can see, using only the brightest galaxies produces very little change. So we have the posterior using just the bright I band galaxies in pink, the bright G band galaxies in blue, and then the full band. And so for best localized cases, not too bad. As localization level increases, the posteriors start to widen, start to diverge a little bit, and that's largely because in the dark side method, what you're kind of trying to do is match your gravitational wave event to a host galaxy, right? So this is relying on individual features in that redshift distribution, both the wiggles and ours. And so as the localization level increases, the contributions to those individual over and under densities of galaxies starts to be washed out. And so the posterior will shift to mimic the overall redshift distribution. This is why a lot of these posteriors are shifting to higher magnetization. Because as you go to higher redshifts, there's always going to be more galaxies. Yeah, and the other thing to take away from this is that the bright L-band galaxies perform a lot better than the bright G-band galaxies. You can see the pink histogram lines up, or the pink posterior lines up better with the pink posterior in all cases. The reason why is because the bright I-band galaxies are actually much better tracers of the overall structure, the overall redshift distribution at these redshifts with the G-bands. You can see pretty clearly here. Yeah. So now we have an idea. Things don't actually look too bad as long as we're in the well-localized regime. We can see how well the bright galaxies actually trace the full line of sight. So to look at that, I found the KS statistic to measure how different two distributions are between the brightest galaxies and the full distribution along the line of sight, and then repeated this for 200 lines of sight to build these systems. So, for example, the pink outlines compare the redshift distribution of the 10% brightest I-band galaxies to the full redshift distribution of galaxies along the line of sight. And so we can see here, small k statistic means things line up well. Those distributions are pretty similar. And so overall, k statistics are low. The red galaxies do a good job tracing the. However, I-band does do better. Consistently lower k statistics. We also see that as an increase the percentage of bright galaxies considered when comparing like the 10% brightest I-band galaxies versus the 30% brightest galaxies. More galaxies, better tracer, we have to import that structure. Right? So now that we have a good understanding of what's going on a very basic level, we can turn to a more realistic analysis. So now we're going to do one gravitational wave in one line of sight, 200 lines of sight. So 200 total gravitational wave events, 200 total lines of sight. This is much more similar to the real data sets that we get from LBK. And so here's a way to read these posteriors. As we go this way, we get more galaxies. So here these posteriors are made using just the 10% brightest galaxies. These are 20% brightest galaxies, and these are the 30%. And as you go down, you get worse localization. So we notice going across the top, the posteriors line up really well. Again, incompleteness has little effect for the best localized events. So that's really useful. As you get worse localization, again, things start to diverge a bit. But the thing to know is that as we go to including more and more galaxies, the posteriors start to look a little bit better. So that begs the question, how many galaxies do we actually want? Does adding more galaxies really even help? So to look at that, I found the pale divergence between posteriors of increasing brightness stars. So what that means is pale divergence is a measure of the difference in information between two posteriors. So a low pale divergence means that the two posteriors have very similar information content. So if we look at that first set of points there, say we just focus on the peak, that's the behind you. We're comparing the posterior made with the 10% brightest I-band galaxies to the posterior made with the 20% brightest I-band galaxies, and then so on and so forth. So again, first focusing on peak here, we see that there is very little information gain after including about 40% of the brightest galaxies. That pale divergence really fucks up, no matter what your luminosity distance uncertainty is. For G-band, things are a little bit of a different story. We can see that at the beginning, we learn a lot as we start including more galaxies. Again, this slows down. And then we see that for larger universes, this jumps up a little at the end. Because at this point, we're comparing the posterior made with the 60% brightest galaxies to the full posterior. So you can see for this case, even at 60% completeness, the G-band posterior didn't quite converge with the full posterior. And that's why you see that jump up. But so again, I-band is performing better than G-band, and including more and more galaxies is useful up to a point. And the reason why a lot of this is working so well, why just using the brightest galaxies isn't actually posing that problem, is because of the impact of large-scale structure. So galaxies tend to cluster to the most massive and thus the brightest galaxies, right? So if you're missing the big galaxies, it's not that big of a deal because there's probably a bright galaxy nearby anyway. So when we're playing this game of dark screen analysis and trying to match our gravitational wave events to potential hosts, if the host is a big galaxy that's not appearing in our catalog, the galaxy you can get matched to is probably not at that different of a redshift, right? And so you're getting these really small redshift differences that are translating to really small changes for each non-posterior. That's why you're still seeing these posteriors line up, even when you're only using 10% of the actual galaxy population. So to test this, make sure that our intuition about how things are clustered in our catalog is correct. Made this by taking say we'll take the 10% brightest I-band galaxies. I drew a 10 megaparsec circle around it and saw how far out in that circle you need to go to capture some X percentage of the total galaxies in that circle. Essentially a measure of how clustered are things directly around that bright central galaxy. And so it is for the 10% brightest I-band galaxies, or a random 10% of galaxies in the sample. And then the brightest 10% I-band galaxies, but in a catalog that clustering. So essentially, I took the same catalog that I've been using, I scrambled up all the RA index to remove large-scale structure, and then as you can see, these differences that are showing that we have very real differences in how things are clustered, and it is these differences that are directly translated to changes on our posterior. So you can see here, if we took our no clustering galaxy catalog, here's the reallocation, what's shown here does not do nearly as good of a job. It's a very real effect thanks to large scale structure. So this has important implications for the future of dark siren analysis. We found out that catalogs don't actually need to be complete. If we have small localization errors, those small localization areas, incomplete catalogs do not introduce a bias on each non-posterior. It's also worth mentioning that using only the 10% brightest galaxies, that's very conservative compared to most galaxy surveys. Usually the redshifts in which we're detecting gravitational waves, our galaxy catalogs are capturing a lot more than just 10% of the galaxies that are really there. Finally, it's also worth noting that really only worth using the best localized events. Worst localized events are going to be more uninformative and more sensitive to the problems of galaxies. In summary, gravitational waves are useful cosmological probes, especially as the number of gravitational wave detections increase, both with LBKs and with the future of next generation detectors. We can actually use them to learn a lot about cosmology. Catalog incompleteness doesn't pose that big of a problem for dark siren cosmology, which is good news, especially for well-localized gravitational wave events, thanks to the effects of large-scale structure. And finally, we've also learned that a stellar mass weighted galaxy sample, bright I-band galaxies, are a better tracer of large-scale structure at low redshifts where we get gravitational wave detections. So that helps inform that some galaxy catalogs are going to be more useful for dark siren analysis than others. So I'm happy to take any questions.
Thanks, Madam, for a very nice talk. Time for questions. I'll start this now.
Spot. Tell me that right. You can never really trust the GDAT. Even at 60% is still wrong.
It's still wrong for these are larger error cases. So if you have a really well localized event, then you're going to be able to trust the GBAD. But yeah, if you know that you have a large localization volume or that your error on the luminosity distance is large, definitely not as trustworthy. Absolutely. But it is also worth noting that this plot is just made by averaging over the results of like 3 sets of gravitational wave events. So your actual posteriors are always going to be sensitive to what your exact gravitational wave events. So it's really going to depend from one gravitational wave event.
How do you interpret the actual value? What's on a scale? So,
Each of these points.
I guess like actual value. What a scale?
Really the interpretation should just be it's kind of quantifying the difference in information between posteriors. Yeah.
So this
How many dark sirens is it?
That's a great one. Hard to say. We only had one bright siren, right? Which was a great one. But let's see. So I think I guess to give you an idea, right now, the amount of gravitational wave detections that we if you use just dark sirens, these are best localized gravitational wave events, you get into H naught posterior with uncertainty of like 15–20%. If you do the dark sirens plus our one bright siren, that uncertainty H naught goes down to about 6%. So the bright sirens are so.
Well, similar lines. It's not tension, you like something like 1 or 2 cones per second. It's like if you have 200 in this video, 100 dark sirens in the localization area in order to get the posterior zero showing. Like, so just how many dark sirens do you actually need to get a competitive H0?
Yeah, I don't know. So currently, like the 6% number that I just said, that's using our best localized events. So I think that was made with around 15 dark sirens and then 1 bright siren.
But they all have to be in the same.
They don't have to be in the same localization volume. That was just me giving an example. So like these posteriors are all made using like different localization volumes, right? So you can still have many different localization volumes and combine posteriors to get a better posterior on each knot. But yeah, but I think it would need to be for hundreds of dark sirens to get competitive.
So it's within reach, perhaps.
Yeah, it was originally thought like, after we got the first bright siren and LBK was very hopeful that we were gonna have more of them, then they thought we would be able to get a competitive measurement in like a decade.
Been waiting almost a decade.
Like then,
Yeah, the question. Thanks for the talk. You talked about how all service levels the mining should limit it, but maybe I missed this. So you are choosing the 10% brightest galaxies, so I absolutely should. Like to me, it seems like if you're looking at the entire redshift sample, you are complete to, a very different absolute magnitude limit compared to very local galaxies. So there's a redshift dependence there.
there is absolutely.
Is it
Yeah.
something like, are you just so local that it's not something you have to worry about?
So yeah, good question. 'Cause yeah, I'm defining incompleteness as like you have X many galaxies, and I'm saying like out of that percentage, we're only detecting some other percentage, right? Where for those people who actually work with like real galaxy catalogs, completeness is more often defined as yeah, you have a magnitude limit at some redshift. You're detecting everything that's brighter than that magnitude. And so for, let me just give you an example. This is like a Blade Plus is the galaxy catalog that was put together for the purpose of gravitational wave cosmology. And so here, these are luminosity distances that we are sensitive to in gravitational waves. And we still see our completeness fall as we get to these larger, at larger redshifts. So it is a redshift dependent quantity, but still most of the time galaxy models vary also so much from one to another, but we're still probably going to have the problem of incompleteness even at the redshift, even at the smaller redshifts that we're thinking about in gravitational waves.
But your hope is that you can always select these 10% brightest things and then you can do it.
That's exactly it. Yeah.
Any other question? Already? Maybe just follow up on very